Good day everyone and welcome to this lecture. We will be continuing with the aeration section where aeration is being used for removal of VOCs, dissolved gases and some amount of metals, some amount of other elements like iron and manganese etc. can be removed by aeration. So, in the previous class we studied how to determine the volume of some treatment unit where some amount of VOC has to be removed. So, in the first case we tried to understand that how to determine the volume in the case where the VOC has to be removed using the surface aeration condition, where a mechanical type of aerator may be used. In the second case we tried to learn regarding a treatment process in which diffused aeration is being used and how to determine the volume of the unit, so that the desired aeration can be performed. So, now we are going to solve a problem related to this and then we will further study another type, very common type of aeration, which is like packed bed aeration, where stripping is being done for removal of any VOC from the water phase into the air phase. So, this is being done. So, we will start with trying to solve a question related to VOC removal, designing a unit. So, in this problem there are certain conditions. So, in any problem in actual condition, though we always give a question which is very simpler, but in actual condition the questions are not simple. Any question has 2-3 sections. One of the sections is like the one which will be given by any industry in simple means. Second section is the one where the learned persons have to go and collect the data from that industry. So, all the parameters have to be determined by us. In the third case, again we have to look into the literature and determine all other known parameters which are required for solving that problem. And in the fourth step, actually we solve the problem, so as to tell okay, this is what is required for your problem and how to solve. So, in this particular problem, suppose the industry is there and it is telling us that they are having already a reactor is there which is having a 2000 meter cube volume, and that depth of the whole activated sludge process is 8 meter, or the aeration unit is only 8 meter, and they are having a flow rate of 6000 meter cube per day of water, and in that particular water the concentration of one of the VOCs is there, and that VOC is benzene and its concentration is 200 microgram per liter. Now, the industry wants that all of the VOC should be removed, and they want to determine that how much fraction will be removed under certain conditions. One condition is that they are using only surface aeration, and in the second case they are only using diffused air system. Now, they are also telling that they have a airflow like a airflow rate, some air is available at a certain flow rate, and that flow rate is 100 meter cube per minute at a standard condition. So, what we have to find out is that determine the fraction of benzene that can be stripped off if the complete mixed activated sludge reactor is considered. So, this is known. Now, we can always find this data from the literature, because for it is given for benzene. So, that means we will have to find out the KLa value, as we know beforehand for solving such type of problem we have to find out the KLa values. Now, KLa values are not easily available. So, we will have to look into the literature to look at the relationships which are available. So, relationship already we have determined that relationship with respect to like finding out for benzene will be like this. So, for benzene this is written. So, we will always look for KLa value with respect to oxygen, and that will be in relationship with the diffusivity value of benzene and also with respect to diffusivity value of O2 up to a certain index n. So, if we can find out the diffusivity of benzene in water, diffusivity of oxygen in water and overall mass transfer coefficient value of oxygen in water, then we can find out the diffusivity overall mass transfer coefficient of benzene, which will be the essentially required thing for solving this problem. Again, for diffused aeration system, we require the Henry's constant also. If you remember, in the previous class we derived the equation for that. So, that means we will have to look for the Henry's constant. So, if we look for the Henry's constant for benzene, its value is this as the one which is reported in the literature. So, we have the oxygen diffusivity value which is given, benzene diffusivity value which is given, and the temperature of whole operation is 20 degree centigrade. The index is already given 1 and Henry's constant is given. Now, we have to solve for each of the conditions. So, for surface aeration only, if suppose we have only surface aeration and in the second case we have only diffused aeration. So, first step is to find out the KLa value. If you remember, the equation for surface aeration was this, and within this the tau value is given by V by Q. So, this was the equation that we derived in the previous class. Now, for finding out the KLa, what we do is that we use the equation that we did earlier, and since all the values are known for diffusivity, overall mass transfer coefficient of oxygen in water is given. So, this is 6.2 per hour and these diffusivity values are already given. So, using the index of 1 we can solve it easily and we can get 2.8208 per hour, or it is like 0.047 per minute. So, this is the first step and we can find out the KLa of the benzene. Similarly, for any other problem we can find out the KLa for any other VOC. If the generally these diffusivity values are given at 20 degree centigrade. So, if we have to find out the KLa value of VOC at any other temperature, then we have to use the temperature relationship as well. So, this is so again we will have to look for some data from the literature for finding out the overall mass transfer coefficient of VOC in that water at maybe elevated temperature of 35 degree centigrade. So, some relationship we will have to look into the literature and get the values of those empirical constant in that particular equation. Now, going further we have to find out the V by Q value, and V is already given 2000 and 6000 is the flow rate in meter cube per day. So, we have 0.33 per day and which is equivalent to 7.992 hour. So, this is now known to us. So, we put all the values in there and we can find out. So, this is like 1 plus, so value we can write down the this value, and remember both the values are in terms of hour. So, we are keeping this hour value here 2.8208 because this value is in hour, and if we solve we can get the fraction of VOC removed. Now, in the second case, okay, I am missing this. So, we can easily find out this value. In the second case, for the diffused aeration system, if you remember the equation was given like this, that the final equation was like this we derived, and for solving this we require HU, we require this psi, and this psi itself is given by this particular equation, and in this KLa is also required. So, we have already solved the KLa, there is no issue. We have to find out the actual flow rate of the gas at that temperature and pressure. So, this we have to solve separately. So, this is being done here. So, we are solving like this. First we have to find out the dimensionless Henry's constant. So, for this we are doing dividing by RT. So, we are using appropriate units so that it is dimensionless. So, this is the first step. Second step is that we have to find out the gas flow rate at the actual condition, and actually in the problem it is given that we have the flow rate outside the system at 100 meter cube per minute at standard condition. So, standard condition it is known. So, what we are doing is that we are using this equation P v is equal to nRT equation. So, P at standard condition, flow at standard condition is divided by T at standard condition is same as P at actual condition, Q at actual condition and T at actual condition. Now, we have to find out this thing. Now, this equation can be changed. So, Q g is actually equal to Q g A c, and this is the equation. Now, what we are doing, we are assuming this both the temperatures to be same. Okay, so, no, here at standard condition it is given 100 meter cube per minute. So, at standard condition it is 273 degree centigrade, and here we have to calculate at 20 degree centigrade, it is 293 Kelvin. So, we are using both the temperatures here, they are not getting striked out. So, both the temperatures are kept. Similarly, we have to know the rho GH condition. So, using this, and we find out pressure at half the height. So, 8 meter is the height of this whole tank. So, but we are finding out average height. So, that is why 8 by 2 division has been done, and if you solve it, actually it will come out 277.06 meter cube per minute in terms of this, as compared to the earlier value which is already given as 100 meter cube per minute at standard condition. So, at this pressure condition this comes out to be like this. So, we can solve it and then we can find out the value of psi. So, this is given here, and thereafter we put the flow rate is given in meter cube per day. So, we have to change in meter cube per minute, so that appropriate units are taken, and overall if you put all the values Q g, H u, psi etc. So, we get to solve and we find that 77% or 0.77 fraction of the total VOC will get removed in the diffused aeration case. So, through this problems we can solve vice versa also. We can always fix it. There is a possibility that we want the fraction of VOC removed, suppose it is desired the efficiency to be 99%. So, this is possible. So, efficiency is known. So, under that condition we have only two manipulations which are possible. One is the volume of the reactor. So, we can vary the volume of the reactor in actual design condition, and second variation which is possible is the flow rate of the gas. So, we can increase the flow rate to remove the efficiency. So, both these two are the manipulating variables in this particular case for diffused aeration. So, we can always play with them so as to reach a optimum condition under which the desired efficiencies can be reached. So, this way we can perform the calculations. Now, going further, there is another type of aeration which is very common. It is called packed tower aeration. So, in the packed tower aeration, wastewater which is to be treated is sprayed on the top of the tower. The tower height may be anything from 3 to 10 meter or little higher or little lower, and is packed with various types of packing. So, these packings are very important because we desire very high surface area to volume ratio, and some of the parameters which are actually used for calculation or for design depend upon this packing. So, what type of packing we are using? So, they may be structured packing, they may be random packing etc. So, this is very important parameter in the packed bed or packed tower aeration. After that, water is coming from the top and air is pumped counter currently from the bottom through the packing from the bottom, and actually while moving up it removes the VOC from wastewater, and which itself is actually being trickled over the packing. So, air along with the VOC gets removed from the top, while treated water is collected at the bottom. So, this is the packed tower aeration. So, this is a simple packed tower aeration, we may write like this. So, water is coming here, it will be having some concentration of pollutant, and this water will go out from here, and its concentration will be reduced to certain value, will be having a air. So, we can write for air some flow rate, it will be certainly having no VOC concentration initially, and then it will be going out at certain air flow rate. So, like Q is generally for the packed bed, it is represented because it is in a liquid phase, we always write generally in L. So, this is in place of Q we write L, and for air generally is in the gas phase. So, it will we write G. So, L and G are common known things, and for this the C out which will be there for the gas phase, this will be equal to G, equal to some particular value, not 0. It will be Q n the concentration which is in the gas phase of the VOC, this will be 0, but this will be certain value which we have to determine, and for that we always want to know that what should be the height of this packing. So, this is desirable and this is actually given by Z. So, the height of the tower can be calculated using the equation which is given here. This is this how to calculate the height of any packed tower for different mass transfer operations, which include aeration, absorption, various other operations, mass transfer operations. So, this is taught in detail in the chemical engineering subjects, in particular in mass transfer or design of mass transfer units. What we will be only studying in this particular lecture will be only a small section of that. So, if anybody is interested in going learning this in detail, they have to study in depth other books related to chemical engineering for better understanding, but still we will get the some idea how to find out the height of the tower for aeration. So, this is there. So, HTU, the height of the tower is multiplication of HTU into NTU. HTU is called height of transfer unit and NTU is called number of transfer unit. So, sometimes they are written like this into NT. So, there are different ways in which they can be. So, it and height is one of the essential parameters that we have to find out with respect to design, and also via using the flow rates, the superficial flow rates with respect to area, actually we have to find out this L and G value. So, L and G value are generally represented as the flow rate per hour per meter square of the bed. So, this is called this is what is desired, and similarly for gas phase also we can write like this. So, and where this meter square gives the surface area, this cross sectional area, and from that we can know the diameter. So, this is how we can find out the diameter of the bed as well as the height of the tower. Now, HTU can be found out using this equation for packed aeration unit or any other. So, where it is the ratio of L divided by overall mass transfer coefficient multiplied by the molar concentration of VOC in that water. So, it is like molar concentration of in the water, what is the molar concentration that we have to determine. So, this is there and it is related to loading rate. Similarly, we can determine the NTU and the number of transfer unit using this formula, and within this formula there is a term which is called as stripping factor. So, stripping factor R is called HU by GL, where HU is the Henry's constant in dimensionless form. So, again HU we have to find out, we have to find out G and L, and from that we can calculate the R value. So, if R value is known and we have the inlet concentration of the VOC and outlet concentration whatever is desirable, and this will be as per the standard. So, if this is known, we can find out the NTU. So, if you have to find out NTU, this is already fixed, only R has to be fixed. Now, if R has to be fixed, HU is already known, because HU for any VOC is known to us. Now, the liquid flow rate is also fixed, because we know at what flow rate the wastewater is being generated. So, that means the G is the only variable that we have to find out, and this G by L, G by L, or we can call it L by G, this is what we have to determine, and this is determined via material balance. So, via material balance we can find out the minimum L by G, and then we can take some L by G value above that. So, we can always have some value idea regarding this G by L or L by G. So, we will understand this when we will solve the problem, where G is the superficial gas flow rate. So, remember the general flow rate is like kilomole per hour, but we are dividing by here meter square, and A is the cross sectional area of the packed bed. So, here A is the cross sectional area. So, this is also one of the our manipulating variable, because we have to find out the diameter of the packed bed also. So, from here we can get the idea what will be the diameter. QG is the normal gas flow rate which is there. So, let us understand little bit regarding how to solve problem. So, here a problem is given that a groundwater is having, we desire a groundwater at this rate for our community, but that groundwater is having a 100 ppm of trichloroethylene. So, this TC is there, trichloride ethylene is there, and which is not desirable, and it has to be removed from 100 ppm to 5 ppb, which is the standard given by different organizations for drinking or for any usage purpose. So, we have to reduce the TC from 100 ppm to this particular value. Now, the tower is packed with 2 inch of. So, this is the thing which the designer does. So, suppose this problem comes to us. So, we will choose that which type of packing we have to use, at what operating conditions, flooding conditions. So, all these things you can learn more in mass transfer operations, which is taught more in detail in chemical engineering. So, you can go there. We have to find out the tower diameter and height. In particular, will be only trying to find out the height for our case, so that we can understand it little better. And we are assuming isothermal operation, density etc. is given. Henry's constant in non-dimensionless form is 248 atmosphere for TC. So, this is known to us. Now, let us put a balance of what is given here. So, in this equation, in this problem, it is given 2.649 meter cube per minute is the flow rate. Okay. In gallons also, because gallons is the common terminology in many countries. So, we can calculate in gallons also, but we are writing like this only. So, this is the flow rate, and this is the 100 ppm, but we want it to be reduced at 5 ppb. So, here L will be the same. Now, we do not know the G value yet, okay, and the out value is also known, but the concentration which is of TC in certainly in the gas is not known, okay, it is 0. So, this is there, and we have to find out the concentration. We are here, remember, everything is written in the mole fraction form for better material balance. So, Xn is the mole fraction of that. So, it can be written in 100 ppm, which is the we can always convert it and it will remain the same. So, 100 ppm, this is 5 ppb, and here we do not know what will be the coming out. So, this is there. Now, if we perform the this is 100 ppm in C in. So, we have to find out the X in. So, X in is being found out here. So, 100 ppm is being converted into mole fraction. So, this is first step. Similarly, 5 ppb which was given here, it is being converted into mole fraction. So, both the mole fraction at x in is known and x actually this is C out. So, we have x out is known to us and this has been calculated in this slide. So, this is 6.82 into 10 raised to minus 10 and this is 1.37 into 10 raised to minus 5. So, we can write like here 1.37 into 10 raised to minus 5 and similarly for x out 6.82 into 6.82 into 10 raised to minus 10. So, this is the mole fraction with respect to liquid phase we know. So, concentration was given, now we have changed into mole fraction. Now, y in is 0 and if we perform the Henry's constant, because for any such type of operations, so we always look at the equilibrium line. So, the equilibrium line is such that this V out will always be in equilibrium with this, because we can have this V out only up to a maximum equilibrium value and this is given by mole fraction. Henry's constant is already given. So, from the Henry's constant we know that what will be the mole fraction of anything in the gas phase if the mole fraction in the liquid phase is known. Now, mole fraction in the liquid phase is known and G value is also known. So, V out, this is the maximum V out possible, but it will never be the same, it will be much lesser than that. It is at this condition that height of tower will become enormous. So, it is not possible. So, what we do is that we try to find out the V out using this equilibrium value. So, V out is known. At this condition we can find out the minimum L by G. So, L by G we can put everything here and you can see here it has been found out to 48.012. So, we can use this value for finding out the actual L by G. So, actual L by G can be assumed like for the gas it is assumed like 4 into G by minimum. So, Y in has been calculated if L by Y, sorry, this is Y out. So, we can find out Y out has been calculated. From putting in the material balance we can find out the G minimum, okay, because the material balance we can always write the material balance equation for this particular case and this will can be written like this: L is equal to C in, sorry, L into X in minus X out and this will be equal to G into V out minus Y in, so mole fraction. So, this is the material balance and using this we can find out the G minimum. So, this is the balance which has been done here and from this G minimum has been found out and from that we are assuming that actual gas loading has to be around 4 times the minimum value. So, once we get this we again do the material balance because the actual is now known here and from that we can calculate the what will be the V out value we are going to take. So, this will be the V out value. So, we have V out value and G actual is known to us. So, we can find out. So, LG minimum was this, LG actual is this 62 and if once this is known we can find out the R value which is given by M divided by L by G. So, this is known. So, this is comes out to be 4 and if this 4 value is known we can find out the NTU because C in upon C out is known to us. So, this comes out to be 12.8. Now, we can find out the H2O also because H2O can be given by this. So, for this particular problem we can if you go and cross check we can put all these values from the literature we are getting the KLa value. Similarly, we can take different values. So, H2O will be coming out to be 3.6. This is not that straightforward, we are assuming lot of conditions here and for better reference we have to go and look out for better books to understand how to determine all these parameters. There are other concepts related to overall height of transfer unit based upon gas side or based upon liquid side. All those concepts are there, but those are beyond the scope of this particular subject. So, we are only solving it to give an idea how to find out the height of the packed bed aeration unit. So, we can multiply this NTU and H2O together and we can get. So, tentatively we are getting this much height. So, we can convert it into the meter also. So, this will be, so what we are getting. Certainly, this value may look to be higher side, because we are presuming a number of things for better understanding. So, this is there. So, this is the preliminary design of any packed bed tower, and we have taken lot of ideas from different books and some data also has been taken. So, all our references are given. So, through this we will end the aeration section, and in the aeration section we have learned how to find out the solubility of any gas in the water. Then we tried to learn the different mass transfer resistances, tried to understand the KLA. Then from that we tried to determine how to find out the oxygen transfer rate. Thereafter we tried to understand the different types of aerators which are used commonly in the industry, and also we tried to solve some problems related to finding out the volume of any unit which will be used for aeration in the case of surface aeration as well as in the case of diffused aeration, and also try to find out the height of any packed bed tower. So, some ideas have been we have learned through this lecture. So, we will continue with other treatment units in the next class onwards. So, thank you very much.